In this video, we are going to design the cantilever beam by using IS 456 2000 codebook rules. We'll see. Design a cantilever beam of clear span 3.25 meter. Service load is 15 kN per meter. Use M20 concrete and Fe 415 steel. And sketch the reinforcement details. What they have given? They are given clear span is equal to, that is denoted as small l, 3.25 meter, and they are given load is equal to 15 kilonewton per meter, and FCK, that is grade of concrete, is 20 newton per mm square, and grade of steel, that is FY 415 newton per mm square. This is the only data we have in this particular problem. So we'll listen step by step by using some rules of code book. So to start the problem, the first step is the effective depth is necessary for all the calculation. We'll go with calculation of effective depth. So step 1 is calculation of the effective depth and width of the beam. And to calculation of the effective depth as per cos 23.2.1a, page number 37, what it says. Let's see what they have said. They have said basic values of span to effective depth ratio for spans up to 10 meter. So for cantilever beam they are given 7. So now we are designing the cantilever beam, no? So they have said the L by D ratio for cantilever beam should not be greater than 7. So I have taken L by D is equal to 7. So I moved D to here and L divided by 7. Clear span we got is 3250 divided by 7. Simplify this, we'll get 464.28 mm. So I am making it approximate value, that is 500 mm. So our D provided is 500 mm. So now the next step is to assume the effective cover, that is denoted as D dash. It is necessary for calculation of overall depth. So let us assume D dash is equal to, I am assuming it as 50 mm. Now we can calculate the overall depth, that is capital D is equal to effective depth plus effective cover. So substitute all the values, simplify this, we'll get 550 mm. So this is how we calculate the overall depth. Now we'll go for the calculation of the width of the beam. So for that we have the formula, B is equal to 1 by 3 D to 2/3 of effective depth. So B is equal to 1/3 of effective depth. B is equal to 1/3 of effective depth, that is 1/3 into our D is 500 mm. So 500 mm, after simplifying we'll get 166.66 mm. So now we'll also calculate the 2/3 of effective depth, that is B is equal to 2 by 3 into 500. Simplify this, we'll get 333.33 mm. So I am making it as 250. B is 250 mm. I am taking the approximate value. So this is how we calculate the width of the beam. So after this we'll go for the next step is to find out the effective span. Next step is step 2 is to find out the effective span. For that, as per cos 22.2 C, page number 35, we'll see what they. So cos 22.2, page number 35, and here C for cantilever beam, what they have said, the effective length of a cantilever shall be taken as its length to the face of the support plus of the effective depth expect where it forms the end of a continuous beam where the length to the center of support shall be taken. What they have said for cantilever beam the effective span should be taken, that is clear span plus effective depth divided by 2 half of the effective depth, that is nothing but d divided by 2, L plus d divided by 2. So L is equal to clear span plus effective depth divided by 2. Substitute and simplify this, will get 3.5 meter. L is equal to. Next step 3 is calculation of the load. So we'll calculate the self weight of the beam. For that we have the formula B into D into rho. Rho is nothing but density of the RCC, that is constant 25. And so substitute all the values, simplify this, will get 3.437 kilonewton per meter. So I am making it approximate value. I am taking 3.44 kilonewton per meter. So after this, so our given load is 15 kilonewton per meter. Now the self weight of the beam plus the given load, we'll add it to find out the total load. So after simplifying, we'll get total load is equal to 18.44 kilonewton per meter. This is our total load. After this, we'll go for the calculation of ultimate load or factor out load. For that, it is denoted as WU. For that, we have the formula 1.5 into total load. Substitute the value. Simplify this, we'll get 27.66 kilonewton per meter. This is our factored load. After this, we'll go for the calculation of the bending moment. For cantilever beam, we have the formula calculation of, for cantilever beam, we have the formula mu is equal to WL square divided by 2. Substitute all the values. Simplify this, we'll get 169.41 kilonewton meter. In terms of mm, that is mu is equal to 169.41 into 10 to the power of 6 Newton mm. This is how we will calculate the bending moment. And next step is to step 5. Next step is to calculate the D required. So D required, the whatever the D we have provided, that is check. We need to check whether that is sufficient to carry this moment or not. By using the formula mu limit is equal to 0.138 FCK BD square. By using this formula, we will calculate the D required. So our D required is equal to under root of mu divided by 0.138 FCK B. Substitute all the values. Simplify this, we will get D required as 495.50 mm. So our D provided is 500 mm. So D required is 495.50 mm. So our D required is less than D provided. So our design is safe. This is how we calculate the D required. After this, we'll go for the calculation of the mu limit. The step 6 is calculation of mu limit. Again, we'll use the same formula which we have used for D check. That is mu limit is equal to 0.138 FCK BD square. Substitute all the values. Simplify this, we'll get mu limit as 172.5 kilonewton meter. So now our mu limit is 172.5 kilonewton meter. Our mu value which we have calculated by using WL square divided by 8, the bending moment value we got is 169.41 to 10 to the power of Newton, 10 to the power of 6 Newton mm. So our mu limit is greater than our mu. So NC, the section is under reinforced. So now we can we can design the singly reinforced beam. After this, we'll go for the calculation of AST. So we have the one formula to calculate the AST without quadratic equation. So I will show by using AST is equal to 0.5 FCK divided by Fy bracket 1 minus under root of 1 minus 4.6 mu divided by FCK BD square into BD. By using this formula, we will calculate the AST. So substitute all the values, simplify this, we will get our AST as 1162.84 mm square. So when you calculate the AST by using the quadratic equation, the answer will be the same when you calculate by using this formula. So you can go either this method or quadratic equation method. And now let's assume the number of bars. I am assuming 20 mm pi bars. To calculate the number of bars required to carry this area of steel, how many number of bars? So I am assuming 20 mm. You are free to assume any diameter of bar. I am taking 20 mm. So now assume 20 mm pi bars. So here we need to calculate the area of each bar. For that, we have the formula AST. Small AST is equal to pi by 4 into pi square. Substitute all the values, simplify this, we will get 314.15 mm square. This is nothing but area of each bar. So now we have to calculate the number of bars, that is AST, which we have calculated. So AST divided by area of each bar. Substitute the value, simplify this, we will get the number of bars, that is 3.70. I am taking the approximate value, that is 4 numbers. So after the calculation of number of bars, we have to calculate the AST provided on this AST provided by using number of bars. For that formula, we have number of bars into area of each bar. By simplifying this, we'll get the AST provided. AST provided nothing but area of actual bars, that is 1256.6 mm square. That is the actual AST. So provide 4 numbers of 20 mm fibers at tension reinforcement. This is how we calculate the number of bars. So after this, so as per clause 26.5.1 A and B, page number 46 and 47, what they have said, there is a minimum reinforcement. The minimum area of tension reinforcement shall not be less than that given by the following, that is AST minimum is equal to BD is equal to 0.85 Fy. By using this formula, we have to calculate what is the minimum reinforcement required on this particular B and D. So we also calculate the maximum reinforcement. The maximum area of tension reinforcement shall not exceed 0.04 BD. We have to calculate what is the maximum reinforcement on this particular formula by using this formula. So we have to satisfy these two to codal provisional. So we'll see one by one. So I have written the same formula which is given on page number 47 and page number 46 and page number 47. So that is AST minimum is equal to 0.85 BD divided by Fy. Substitute all the values, we'll get AST minimum as 256.02 mm square. This is the AST minimum. So now we add to the maximum. We have to calculate the maximum reinforcement. That is AST maximum is equal to 0.04 BD. This formula is given on page number 47. The same formula I have written here. Substitute all the value, we will get 5000 mm square is our AST maximum. So what they have said we should not provide AST less than 256 mm square and more than 5000 mm square. So our AST is in between these two. How much our AST is? So our AST is 1162.84 mm square. So it lies in between these two, so that we have satisfied these two codal provisional. AST is greater than AST minimum. Hence our design is safe. We can proceed further. So this is how we calculate the AST minimum and AST maximum. After this, we'll go for the calculation of shear reinforcement, that is shear force. The step 8 is calculation of shear reinforcement. For that, shear force, for cantilever beam we have the formula Vu is equal to WUL. Substitute all the values, simplify this, we'll get 96.81 kilonewton as shear force. And next step is to calculate. So next step is to calculate the nominal shear stress, that is denoted as tau V. So we'll calculate this as per our codal rule. What it says, as per cos 14.40.1 page number 72. What they have said, we'll see. 40.1 nominal shear stress. The nominal shear stress in beams of uniform depth shall be obtained by the following equation, that is tau is equal to Vu divided by B into T. By using this formula, we will calculate the nominal shear stress. Let's see. So the same formula which is given on page number 7.